Okay, good morning, everyone. This is our lecture 12. So in the beginning, I'm going to correct a mistake I made in the last lecture. It's about a wall test. So basically what I said is that you take the variance covariance matrix inverse first, and then you take the block. That's not correct. Yeah, I checked that and I found I made a mistake here. So here we should move this, okay? We should get rid of this and we should put an inverse here. So we're just taking the block for the beta 2 hat, okay, for beta 2 hat, which corresponds to the P2 by P2 block here, and we take it out, we take its inverse in the wall statistic formula. Yeah, this should be the correct. And what I said last time was wrong in that we shouldn't have the variance of other estimators to interfere with the variance of this estimator in the inverse. That's not right. What I want to say is that we should consider when we calculate this V22 in the variance covariance matrix, this calculation depends on how many parameters we are going to estimate in beta. So if beta is a very high dimensional vector, then the estimation uncertainty or the variance here will all be inflated. That's something we call the curse of dimensionality. But if you only estimate, say, those P2 by B2 coefficients only, then the variance for this P2 by P2 matrix will be different. So that's what I want to say. But we shouldn't take the inverse of the whole variance matrix first and then take the block. That's incorrect. What we should do is that we take the block from the variance covariance matrix first, and then we take the inverse of the block. That's the correction I want to make for the wall test. And so in the recording of last lecture, I posted the Wikipedia link to wall test. I suggest that everyone reads it. It's very informative. It talks about the wall test and the likelihood ratio test. We covered both in our class. It also talks about something we don't cover, the score test, okay, which relies on the score function, which is the gradient of the log likelihood, and the Fisher information relies on those two things to construct a statistic. So we didn't cover that. So what's the advantage of the wall test in relation to likelihood ratio test? I think the Wikipedia make a very good point. That is, when you compute a wall test, in the pre-computer age, this is computationally advantageous because you only need to run one regression on the whole model, on the full model, and then you take the beta 2 hat from there, you take the covariance matrix estimator from there, take the inverse. So you just run one regression. While in the likelihood ratio test approach, you need to run two regressions. One is a reduced model with only the predictors in X1. One is for the full model. So that's not easy if computation is a concern. But now, since this is no longer a concern, we prefer likelihood ratio test because it is more general and also it has very nice asymptotic property. Yeah, so I think that's the key distinction. So if you want to know one thing for now, probably you should know likelihood ratio test. Okay, so that's just the makeup for the last lecture. And today we're going to continue our discussion about GLM. So there's an important property I didn't say yet about the exponential family GLM with canonical link function. So I'm going to emphasize that as the first topic today. So an important property of exponential family. As a recap, this is about a random structure, GLM, with canonical link function. And the link function is what we need for the systematic structure, right? So this is for the random part, and this is for the systematic part. And what this says is that if you go for the canonical link function, then the systematic structure is automatically determined by the random structure. As long as you specify the distribution, you would immediately have the canonical link function. just as what? As the B prime inverse, right? B prime is the derivative of B function in that exponential family density. And that B can correspond to different functions for different distributions. But once you have that, you take its derivative, you take its inverse, then you immediately have the system, the link function. That's what we call the canonical link function. And then what's the important property? The important property is this: X transpose Y. So we know this gives us a P by 1 vector, okay, together, is equal to X transpose mu hat. Again, this is a P by 1 vector. So we have P equations, in other words. And how do we derive this? This can be seen from the MLE, right? We know that we use MLE to estimate parameters. And given that beta hat, with transformation, we can obtain this mu hat. So we'll go from that route to see how this can be easily proved. So the log likelihood of beta, which is our key parameter of interest, has this form: lowercase l equals I from 1 to n. I'm writing the log density of exponential family. Yi is the observation of the ith response. Theta I, the location parameter, minus b theta I divided by a phi. Phi is the scale parameter. AI phi, sorry, I should put I here for the ith observation, for the ith distribution, and plus c yi phi. So we are assuming that phi has nothing to do with observation I. It's a common scale parameter, and the location parameter changes with I. That's our assumption. Okay, then given this likelihood function, and given that we have canonical link function, so using canonical link function, we are assuming theta I equals eta I. This is what we mean by canonical. And eta I is what we call the linear predictor. So using this, you can immediately see that I would have yi eta I minus b eta I ai phi plus c yi phi. Okay, and then I'm going to use the fact that eta I is equal to xi transpose beta. That's the definition of linear predictor for eta I. Okay, so we're going to put eta I in, and we can see that we would have yi, a scalar, times xi vector transpose beta. We have an inner product between xi and beta, and minus b xi transpose beta. Denominator stays, last term stays. And my interest is beta. So I'm going to take the gradient of log likelihood with regard to beta. So in order to do that, we know a gradient here is a vector whose dimension is equal to the dimension of beta. So it should be p-dimensional. So what we do is that we need the element, each element of the gradient. So that we call that a partial derivative. So we have partial L, partial beta j against the jth component. Okay, and we can clearly see that what we would have here in the sum, we keep the denominator. In the numerator, we know xi transpose beta, in that inner product is actually the summation of xij times beta j for j. So when we take the partial derivative against beta j, we get yi times xij. Okay, the ith row, jth column of the design matrix. And for the second part, by the chain rule, I am going to get still xij out times b prime xi transpose beta. So you have that. And you see, what's interesting, and I'm going to set this to 0, okay? I want this to be set to 0. So in other words, this will tell me that I would have the summation I go from 1 to n, yi xij, okay, equals, I move this part to the right hand side. So I go from 1 to n, xij times b prime xij, xi transpose beta, sorry. And then what is xi transpose beta? I know it's eta I, and I know it's theta I. So I should put the hat here so that I know this is something I should satisfy with my MLE. So I should put a hat here, and I should put a hat here. So my MLE should satisfy this equation. And then I can say that this further gives me xij b prime theta hat I. Okay, I'm just going back to the theta hat I. And I know that this b prime theta hat I is the expectation of yi with the MLE, with that property of exponential family. We know mu I equals b theta I. But here we're using theta I hat, which means it's the MLE of theta I. So we can say that b prime theta I hat is mu I hat. So I go one step further, I get, okay. So you see, what I have here is for the ith element, I'm going to have this thing. So for the ith element, I have the xij times mu I hat, and I'm taking the sum over I. So this is what? This is essentially, so the left-hand side, let me write this way. You can see I'm taking basically the inner product of the y vector with the inner product of the jth column of my design matrix. I call that xj. So I'm just going to remind you that if I write x as this x1 to xp, okay? So columns, each column is called, jth column is xj. So this is the jth column with inner product with y. So we can actually write it as, so let me see. So we can write it in this way. So I can say that this is xj transpose. So the jth column, I take the transpose times y. Okay, that's the inner product. And over here, I can do the same thing. Xj transpose times the mu hat vector. So I have these two things equal for every j, because I need every partial derivative to be 0. J go from 1 to p. So you see that for every j, I have this. And this is what? This xj transpose is actually the, let me write it this way, x1 transpose to xp transpose. You know that when I write the columns, I use the capital X, capitalized X, and when I write the rows of X, I use the lowercase x. So here, X transpose can be written in this way. Then you can see Xj transpose is the jth row of X transpose. So by stacking them from 1 to p, I would have X transpose times Y equals X transpose times mu hat. So this is the conclusion. And this has a name, right? This is a very important result. I think this is called the normal equation. So for exponential family GLM with canonical link function, we always have this. And we used to know that this holds for least linear model, right? When we do least square for linear model, we have this property. But now we know that for a broader class of model GLM, as long as you use exponential family for the random structure and use the canonical link function for the systematic structure, you still have this property. And because we know the first column of the design matrix contains ones, so that the first row in X transpose contains ones. Therefore, we would have a one vector, you see. So remarks. The first remark is that we know the one vector, n-dimensional one vector, inner product with y equals this because of the first column in the design matrix. So this tells me what? This tells me if I take the average of my response, it will be equal to the average of my predicted response of my fitted values. So in the linear regression, you know this fact, right? Y bar and Y hat bar, they must go through the same dot, same point. We know that. And here we also have this for the GLM. And furthermore, if we have a factor as our predictor, that is, in the case of ANOVA, if you recall, we talk about a predictor being a factor, right? And if there's a factor, let's say with 2 levels, then in the design matrix, we would have a column corresponding to level 2. And that level 2 will give zeros to observations in level 1 and ones to observation in level 2. So then you can show that by multiplying that columns transpose with y and with mu hat, you are going to show that within each level, the sum of the y's will be equal to the sum of the mu hats. Okay, so let's say this is the general thing. And then the second thing is that if there is a factor, or we can say categorical predictor, okay, then within each level I, we would have this, the summation j from 1 to ni. This is the notation we used before. Ni is the number of observations in level I. Yij equals j from 1 to ni mu ij hat. So we also have the within group property. Okay, so that's the property I want to introduce here. And this is often nice for sanity check. If you're unsure about whether your model fitting is correct, you can always check this to make sure. Okay, do we have any questions about this part? Okay, so now let's move on to our second GLM model we want to introduce, in addition to logistic regression. This is what we call Poisson regression. Okay, and Poisson regression is going to be used for count responses. So what do we mean by count responses? We mean that each yi is a count. And how is this different from the group data for logistic regression? So in the group data, you know that, okay, my count yi has a maximum as ni, right? You remember that yi follows binomial ni pi I. That's for the logistic regression for group data. And so in a concrete example, that means if I have ni people with the same covariance like age, gender, education level, etc., then among those ni people, I count how many of them voted yes in an election. Then that yi is my response. So I know the yi cannot be bigger than ni. That's for group data. But for the Poisson regression, we don't know there's an upper bound. So for each yi, we only know it's a non-negative count, but there's no upper bound on how large yi could be. Okay, so here the random structure is that yi follows Poisson mu I. We know that in theory, a Poisson random variable can be as large as possible, as large as infinity. But we know that depending on the mu I, we will have very, very small property to observe a large value. The smaller the mu I, the smaller the probability that we're going to observe a large count. Okay, and then given the random structure, we can actually write down its corresponding form of the Poisson distribution using the exponential family density, using this form. And then we can show that the canonical length function is a log function. This is, I think, in your homework to verify what's the form for the Poisson. So then we have the length function as the log, and we assume this is a linear predictor. So this is xi transpose beta. So this is quite straightforward. Now we understand the logistic regression. There are two major changes. One is from Bernoulli or binomial to Poisson. The other is from logit function to log function. And you can also see why this makes sense intuitively, because the Poisson parameter is required to be positive or at least non-negative. When it's 0, then we stay at 0. So that's the Poisson parameter requirement. And when we take the log transformation, we are converting a non-negative mu I to real numbers. So that matches the range of xi transpose beta. Okay, so now how do we do the parameter estimation for beta? We can show the IRLS algorithm for Poisson regression. So let's just do that again. IRLS to estimate beta. So we will first start with initialization. So let's say that we have some parameters to start with already. Then given the parameters, we are going to find what's the working dependent variable and what's the weight matrix before we run the weighted least square to update the parameter values. Okay, so let's just write here. So in the kth iteration, we first need the working dependent variable. So this is going to be our actual response in the weighted least square. And we give it a name as ZIK. K means the iteration, and I is the ith observation. So if you recall, what we have here is based on the current linear predictor eta I and a remainder term yi minus mu ik times g prime mu ik. Recall that this is actually from Taylor expansion. Okay, and then we need this, right? We need g prime. What's g prime? So g function is the log function. So we know that given g mu I is log mu I. So we know g prime is 1 over mu I. So that will give me eta ik plus yi minus mu ik times 1 over mu ik. This is how we can get the working dependent variable. And the second thing is to get the weight matrix. Okay, for the weights, let's say for the ith diagonal entry in the weight matrix, so we know its definition is equal to 1 over the variance of zik, of the working dependent variable. So based on this, we know that it's equal to 1 over the variance. So actually I should, to be more precise for this variance, because the variance itself involves the parameters. So I should put k as a superscript for the variance, because variance itself is not a parameter-free thing. Okay, so then I would have the variance to be computed using the current parameter values for yi times the square of this constant. So I would just say 1 over mu ik square. Okay, so then the only thing I need is the variance k of yi. And Poisson gave us an easy answer. We know the Poisson yi for yi Poisson, its variance is just mu I. So we know that this is mu ik, and it can cancel one mu ik here. So I'm left with 1 over mu ik in the denominator. I take inverse, so I get mu ik. That's the weight. Okay, so then we do the update. That's where the weighted least square comes in. So beta k plus 1 is x transpose wk x inverse x transpose wk zk. So I'm going to update my parameter as this, first to get the beta, and then I update the linear predictors. Eta k plus 1 equals x design matrix times beta k plus 1. Okay, I have eta. So, with this, I have the eta I k plus 1 for my next round of working dependent variable. And I also need the mu. So the mu k plus 1, or I should say mu I k plus 1. I know this is based on the inverse of the link function, right? Mu I, so we have the g mu I equals eta I. So then mu I would be equal to g inverse eta I k plus 1. What's the inverse? Here the g is the log. The inverse of the log is exponential. So we have exponential eta I k plus 1. And we do that for each I from 1 to n. And that's it. So this gives me the update parameters, and then I go back to the working dependent variable and the weights and to continue the iteration. So you see that in terms of the formula, the IRLS for Poisson regression is actually simpler than for logistic regression. And also one more thing I want to say is about the Poisson distribution itself. So we know that the Poisson distribution can be regarded as an approximation of binomial distribution. Probably I should write it here. So I can say that if we compare this to yi follows binomial ni pi I. Okay, so if we compare this random structure to the other structure, we know that this this distribution would converge to the Poisson distribution that is equal to what ni times pi I if ni is going to infinity and pi I is going down to 0. And while the ni times pi I converges to some constant, okay? So whenever this happens, the Poisson distribution is an asymptotic limit of the binomial distribution. And you can see the intuition behind this. That is, when your ni is going to infinity, it means that in theory, pi yi can take very, very large values. And that is consistent with Poisson. There's no actual limit. But the pi I need to go down to 0 so that ni times pi I, which is the mean of yi, is not exploding. It's converging to a constant, which we call ni pi I. And that constant is just the mu I in Poisson. So in other words, we need to have a decreasing probability of getting 1, that's pi I, to counteract the increase in the number of people here, ni. So that when ni times pi I, the expected number of people who vote yes will converge to a constant. Yeah, so you can see in some real problems, if you believe that binomial is the data generating mechanism, but if you believe the total number of people is super large and the probability of voting 1 is super small, then it makes sense to use Poisson to approximate binomial distribution. And Poisson has a simpler probability mass function, especially if you think about, if you know the stochastic block model for network analysis. So in that case, when people want to incorporate, so to step back a little, so each edge is assumed to be a Bernoulli random variable with 0 or 1, right? 0 means no edge, 1 means there's an edge. But if you want to incorporate some degree corrective version for that, so that each node is going to be weighted by the degree, then that Bernoulli becomes quite complicated. So in that field, people just use Poisson for easier likelihood. So use Poisson as approximation. Okay, so this is the Poisson regression for count responses. So for Poisson, we also can have group data. So same as our logistic regression. So the group data is just happens whenever we have observations that share the same covariate. So now let's look at group data. Okay, so let's say that we have group I that go from 1 to n, and we have ni as the number of observations in group I. So for observations in group I, they share the same covariates xi. Okay, so they share covariates xi transpose, the ith row in the design matrix. So in other words, if you think of the before grouping and after grouping design matrix, so I would just say probably this is something, if I call that before grouping, and let's say if I have ni rows that are exactly the same, then after grouping, I'm going to just come, so it used to be a block, but I'm now going to condense it into one row. Okay, I call that xi transpose. So you see previous I have xi, xi, so a repetition of ni of them, but now they're condensed to one row. So it's essentially, you can think of each row in the group data corresponds to ni rows of the before grouping data. So how many rows do I have here? I should have summation of ni, I from 1 to n. That's the total times P. That's the before grouping design matrix. But now after grouping, my dimension is reduced to n by P. So let's keep this in mind. Okay, then correspondingly, I need to group my responses, right? So I would say in group I, the responses, I write them as yi1 to yi-ni, a total of ni observations. And after grouping, I'm going to take the summation. Just add them up, call it yi. So it's the sum of yij, j from 1 to ni. And whenever these are independent, okay? So by assuming these ni observations are independent, then after grouping this yi as a sum of ni independent Poisson variables, it's still Poisson, okay? So it's still a Poisson distribution, and its mean is actually the mean of each one, take the sum. So if we assume the same random structure as for the individual data, that is, here we have each yij, each yij follows Poisson mu I. Yij are IID with Poisson mu I. So for j, go from 1 to ni. Then after taking the sum, this Poisson will be equal to ni times mu I. So you see, under this assumption, I'm stick with the same random structure for the individual data. So to put it here, so the random structure, now I write it for the group data as yi follows Poisson ni times mu I. And this is consistent with individual data. So this is from Yij, IID, Poisson, MUI, from individual data to group data. And for the systematic structure, I use the same as the one for individual data. So still log mu I equals xi transpose beta. This also stays. Okay, that's it. This is the model for group data. Then the question is, what do I have here? So how do I estimate the parameters? Okay, so if I want to estimate the parameters using IRLS, will I get the same beta estimate? Actually, the answer is yes. So will beta hat MLE be the same for individual data and group data? The answer is yes. And here we're going to see that. So which means that if you don't stack your observations, but just use the original individual data design matrix to run the individual data Poisson regression, versus you combine the repetitive rows to have this group data design matrix and run Poisson regression on group data, you will have the same estimate for MLE, and also the MLE will have the same variance. So nothing is changed. But this group data is obviously computationally preferred, right? Because you can much reduce the number of rows, and that can save you a lot of storage and also your computational resource for matrix multiplication, for example. So for this systematic structure, I want to say that although this is consistent with individual data, but another way to write it is to write it as the log of the expectation of yi, right? Because this is the mean of yi, and our systematic structure is always about the mean of yi here. So, but here the mean is no longer mu I. It's actually log ni mu I. So we have a log ni out here plus the log mu I. Log mu I is the linear predictor xi transpose beta. So in other words, in some places you will see, okay, for group data, we have an offset term. When they say that, it's referring to this log ni. It's just when you write a systematic structure in terms of the mean of the yi, of the grouped response, then there's an offset in addition to the linear predictor, xi transpose beta. And you see this offset becomes zero when your ni is 1. So that's the individual data case. When you have individual data, there's no offset. Okay, so just a terminology. Then let's come back to the question. So why would MLE stay the same? So we can try to derive the working dependent variable for group data. Okay, and then we can compare with what we have for the, we can compare it with what we have for the individual data. So let's see, let's look at the IRLS for group data. So still, let's first look at the working dependent variable. So in this case, we have the zik, okay? So zik, what is that? It's still two-part. One is the eta ik, the linear predictor, and the other is the yi minus mu I times g prime mu ik. So I would say for simplicity, probably we should just consider the eik to be the linear part as well. So that, which I mean that when you do this, you don't need to worry too much about offset. So let's talk about the working dependent variable still on the scale of individual data rather than on the scale of group data. So still consider this to be, how should I put it? Okay, never mind. Sorry, I take my words back. So let's just use the EI. Okay, so eta I. So here, let's still define the eta I. This to be the eta I. Okay. So let's still have the eta I just as the linear predictor. I think that's fine for us. So the zik is still eta ik. And then for the yi minus mu ik. So here it is for the group data. And let's take a look. So yi is the response, okay? And its mean is now not mu I, but ni times mu I. So this mean should be changed to ni times mu ik. And then by Taylor expansion, this G prime should be G prime at ni times mu ik. We always have the differentiation at the value we want to expand it for. Okay, then you can see something similar, something interesting. So the G function, what is G? This is still the G. G is still log. So when I take the G prime, it's still 1 over the argument. So you can see that for the second term, I will basically have yi minus ni times mu ik divide times 1 over ni mu ik. So you see what happens here is that eta ik stays, it's just xi transpose beta. So it's not for grouped. It doesn't have the ni with it. It's just as if it's for one observation. It's just the one row times the beta. And for here, you are going to cancel out ni here. So you would have basically yi divided by ni. It's the average of group I minus mu ik times 1 over mu ik. So what I mean that in terms of the scale of zik is on the scale of one individual data point. So in other words, it doesn't carry ni with it. Doesn't carry ni. And you can see from the combination here, when we do the combination, we just take each xi to be the row. We didn't take the sum. We are not saying this row is ni times xi transpose. So that's why if you just look at this row, you regard it as one individual data point. And that's why here in the eta ik, it doesn't carry the ni. And here, although we have ni in yi, ni in this term, but after the cancellation, we still left with a term not involving ni. So ni is not there for the number of observations. You just use the average. That's for the working dependent variable. Now let's look at the weight, okay? The weight is something interesting. So for the weight, wik, still it's 1 over the variance of zik, variance k for the current parameters. So now we see what's in the random variable. It's here. The second term is random. First term is not regarded as random. So what would be the variance here? You see, it's actually equal to, I have yi divided by ni times mu ik in the denominator. So basically, I have the variance of yi times the square of ni square mu ik square. Okay, and the variance of yi based on the random structure Poisson ni mu I. Ni mu I cancel one copy with Ni mu I here. So I'm left with, let me see if I'm correct. Variance. Yeah. So I have whenever, oops, my bad. I missed this part. Sorry. I should have this in the denominator. My bad. So this is Ni mu I. Cancel Ni mu I. I left one copy. I take inverse and inverse again. So I'm left with Ni mu Ik. Okay. So that's WK. Now you see W carries Ni with it. But now let's look at the beta K plus 1 update formula. So this one has X transpose WK X inverse X transpose WK ZK. Okay, so what we have here is WK's here and here. Now what does it mean? Let's take a look at X transpose X without W, or with for the previous one or for the current one. So you see for the individual data, let's take a look at what's X transpose. So for X transpose, we would stack them as this. So we have, originally we have the rows as our observations. In X transpose, they would become, let's say, the columns. So let me think about an easier way to say this. X transpose WK. So maybe let's say this. So we would have XJ individual data. So let me see this. XI transpose blah 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 to XP transpose. And I should say these are the individual data. So probably I just mark them in another way. So I just okay, let me just say this. Individual data have X star. Okay, so I will carry X star with everyone here. And so previously in that case, the W matrix is just a diagonal matrix. So I'm going to put it here. So mu 1K to mu, I call capital NK. That means I take the sum of all individual data. So coming back here, probably I just give you a notation. So I call this part as capital N, the number of individual data. Okay, and what I would have here is just XI star transpose to XP star transpose. Yeah, I should put star here. So you know what I mean. So this is what I would have before the inverse. This is what I have for individual data. And then if you compare this to group data, what I would have is XI transpose to XP transpose. Now the weight matrix become N1 mu 1K to N, what's the total? NN, yeah, mu NK. And each of them is just a few of them that with a sum. Okay, so we know that some of them are repetitive, so I'm going to combine them along the diagonal. So, or probably to help you better understand, I'm going to have a few mu 1K here, and the total for that is N1. So that can help you better understand the distinction between here and here. And also in the left matrix, each XI star transpose is just longer than X1 transpose. So it's just like I'm going to combine its repetitive elements in the group I into one entry here. So the right matrix is X1 to no transpose. X1 to XP. Okay, so then you can see what? By this matrix multiplication, you can see that essentially I'm going to have the X1 star transpose times X1 star. So I'm going to have the squares. So like for each term here, I am going to square it and then take the sum. But I know that among the square, a lot of them are repetitive, so that they are going to be multiplied with the same mu1k for ni times. So I have n1 such terms. And now in the group data, I'm just combining them into n1. So in other words, these two products will be exactly the same, equal to each other. So this is the first thing you need to see. And furthermore, for the second term, for this term here, also you see by adding ni to the weight matrix, I'm basically given each xi, sorry, each entry here, each column here in the X transpose correspond to one observation in the group data. Each observation group data is going to be assigned with the weight ni. So it is as if we still have ni individual observations. And because the zk doesn't carry the ni in its unit or its scale, so therefore, when we multiply X transpose wk zk, it is also equal to what we have for individual data. So in other words, this update formula stays unchanged after grouping. Unchanged after grouping. So no wonder that data will converge to the same estimate regardless of whether you use the group data or individual data. And using group data can save computation. I hope that makes sense. Okay, so if you really want to think deeper into this, it's basically a linear algebra thing. Okay, and then for the inference, right? So previously we have beta hat follows asymptotically based on the large sample theory or central limit theorem variance is following a multivariate p-dimensional normal distribution with mean beta and the covariance matrix as X transpose W X inverse, and this W is going to be based on our MLE estimate. So that's something we do the plug-in so that this unknown parameter is achievable. Okay, so with this, you can see that given that we say X transpose WX stays unchanged after grouping, so this distribution also holds for group data. So this also stays unchanged after grouping. Okay, so the take-home message is that when we do grouping by combining observations with the same covariates, we do not change our model parameter estimation, and we don't change the model parameter inference. That's the take-home message. Okay, and so another part I want to say is about the goodness of fit test for Poisson regression. So still we have two approaches. One is to use the deviance statistic, right? That compares what we have from the GLM with the saturated model. And the other is to do the Pearson's chi-square statistic to compare the observed counts to the expected counts under GLM. So it's basically the same as what we discussed before. So I'm not going to go into the detail here, and you can check the notes. So the goodness of fit test can also be done for Poisson regression. So I'm going to skip this part. So what I'm going to talk about next is the limitation of Poisson regression. As you can see, the Poisson assumption is quite strong. It's a one parameter distribution, which requires that its mean equal to the variance. Both must be equal to mu I. That's a quite strong assumption. And in reality, our data may not satisfy this assumption. So when this assumption is clearly violated, when you fit the Poisson GLM to your data, the goodness of fit may be bad. Okay, so that's why the goodness of fit is very important to check how does the Poisson GLM fit to data. And we know that we do not want to reject the null. When we have a very small p-value for goodness of fit, it indicates that our GLM fits poorly. So in that case, we need to think about some fix. How do we fix this model poor fitting? So this is a common issue for count data. So we say that here we could have count data with over-dispersion. So by saying over-dispersion, we mean that expect a variance of yi is greater than expectation of yi, which violates the Poisson assumption. And then how do we fix it? So we're going to introduce two approaches. One is what we call the Extra-Poisson model, and the other is called negative binomial model. So these two are both models for count data, and they can fix this over-dispersion issue. So let's start with Extra-Poisson. By extra, you mean that we're considering extra variance. And here we're going to Extra-Poisson regression. We're going to introduce a concept in classical statistics called Quasi Likelihood, which means that it's not a real likelihood, but we can use it for parameter estimation. And the Quasi Likelihood approach was actually proposed by a person who has made a very significant contribution to the GLM called Wedderburn, his last name, in 1974. So he had two papers, I think, in his career. Both have made a big impact on the development of model parameter estimation for GLM. But unfortunately, he passed away at a very young age. So that's why he only left those two works. But still, we memorized him because of his significant work. So the quasi-likelihood, I think, is a very interesting thought. That is, we still want to utilize the likelihood or log likelihood function for Poisson regression, but we want to allow the variance to be different. So we don't want to stick with a contingency that the variance must be equal to the mean. Okay, so what they want to specify. So the idea is to, in the random structure, so drop the requirement that variance yi equals mu I in the random structure. Okay, but after we drop this requirement, what is the distribution of yi then? So the thought here is we don't care about it. We don't specify the distribution of yi. Instead, we just let the variance to be a free parameter. So to do that, we give it a notation. We specify the variance of yi. We denote it as v mu I. Okay, that's the notation we're going to use. And then it defines the quasi-likelihood of quasi-likelihood. So they just say for each yi and its mean parameter mu I, it defines a quasi-likelihood called k yi mu I by its derivative. So we define the quasi-likelihood of d k yi mu I, or I should probably write partial. Yeah, I think that's better because I have yi here. Partial mu I. This is defined to be yi minus mu I over v mu I. Okay. With this definition, then we can say, okay, the function k is a quasi-likelihood. In other words, as long as the function k satisfies this, you say it is a quasi-likelihood. And what's the motivation? This is motivated by the log likelihood of exponential family. So when we say yi follows a one parameter exponential family with only one parameter. Okay, so maybe I can say it as just theta I. Okay, so that we don't have a scaling parameter. So no scale parameter, just the location parameter theta I. So recall what will be the log likelihood here. So we can see that the log likelihood of, if we write it as mu I, okay, mu I is the mean of yi, then the log likelihood is just the log of the density of yi given theta I. So that's actually log of the exponential density. That's what we have for exponential family. It's actually yi times theta I. We are familiar with this, minus b function of theta I. Previously, we have the scale parameter, right? We have the ai phi, but now phi is not there. We just write ai. And for the last part, used to be yi and phi. Now we just write yi as the only thing in the C function. So this is what we call one parameter exponential family. I should say one parameter. One parameter. Yeah. And then you see, if I take the derivative, dl mu I d mu I, clearly log and exponential are canceled. So when I do that, I would have what? I would just have, I should do dl d theta I, right? Because it's in terms of theta I times d theta I d mu I by the chain rule. So for the first part, when I take differentiation against theta I, I'm left with yi minus b prime theta I divided by ai. And for the second term, because I know the property that mu I equals b prime theta I, so this tells me if I do d mu I d theta I will get b double prime theta I. And then what I need is d theta d mu I. I take the inverse. So in other words, I am going to, because of this, okay, the second term is going to be 1 over b double prime theta I. Yeah, this is just a note, but what I really want to have is this. So you see it's here. So combining the terms, I would have yi minus b prime theta I, ai times b double prime theta I. And I know that it's in the denominator, it's the variance of yi. That's also by the property of exponential family. So I have yi minus mu I divided by v mu I, right? By our notation, v mu I is variance of yi. So we're done. So you see, for the log likelihood of one parameter exponential family, its derivative against mu I is of this form. Now, when we define quasi-likelihood, we just borrow this form by defining, okay, the quasi-likelihood's derivative against mu I should be the same as what we have for the one parameter exponential family. And then we just have the quasi-likelihood. So in other words, we don't have any specific assumption on what is V mu I in quasi likelihood. We just say, okay, there is a variance in the denominator, the mean is in the numerator. So it can be regarded as a generalization. So this is a generalization of log likelihood of one parameter exponential family. That's what we have for quasi likelihood. And for this quasi likelihood definition, we also have some properties that are similar to what we have for the log likelihood. So you see this term, this differentiation can be regarded as the generalization of score function, because we know the score function is the derivative of log likelihood. So we also have it here. So therefore, we would have several properties, including, so I think it's interesting to introduce them. So we will conclude today's lecture by talk about these properties, okay? Properties of K, Y, I, mu I, the quasi likelihood. The first thing is just as the log likelihood. Its derivative against the parameter. So partial K, partial mu I, yi mu I. When we take the expectation, this is for the random variable yi, it's 0. Okay, so just as I said, it's very similar to score function. For score function, we also have expectation 0. And the second property is, what if we're taking expectation not, or we're taking partial derivative not against mu I, but against beta j. So the second thing is expectation partial beta j. We know that because we're still under this GLM framework. So we have mu I equals to, I should say G mu I equals to xi transpose beta. So this is still what we have for the systematic structure, xij beta j. So this is still what we have. So when we take this partial or quasi likelihood against beta j, because this is what we're gonna use for parameter estimation, right? When we want to set this to 0 to solve for the beta j as MLE, that's what we need. So this expectation is also 0. And we can see this clearly because we know that partial k partial beta j is simply partial k partial mu I partial mu I partial beta j, right? It's just this. So we know that the second part is just xij. And in our context, this is fixed. So the randomness is only here and here. In other words, when you take expectation, the expectation is going to be around the first term only. So that's why when it's 0, this is 0. And the third property is something like our Fisher information. So when we take the quasi likelihood for twice differentiation, that will give us what we call as a Fisher information. So we still have this property that if we take the Fisher information, so partial square k twice partial mu I square, okay, yi mu I. Now this is a scalar because mu I is just one-dimensional, and this is equal to the expectation of the square partial mu I kyi mu I. Okay, and we know that this is equal to 1 over the variance of yi, v mu I. So previously for the Fisher information, we have this. So that used to be the variance of yi. But now given our definition of the quasi-likelihood, based on this definition, we still have this property. That is, Fisher information is the negative of twice derivative, and it is equal to 1 over the variance, the random variable that follows the distribution. And this is also equal to the expectation of the square of the score function. So this is just like what we have for Fisher information. We have an analogous concept or property here. Okay, and the fourth thing is that what if our differentiation is not taken for mu I, but for beta? So that will be, so if we take the twice differentiation against beta, that will give us a P by P matrix, right? And that is called a Hessian matrix. Then what is that? That's the fourth property. So for the jkth entry in the Hessian matrix, partial beta j, partial beta k, yi mu I, still it's equal to the expectation of the outer product of my two gradients. So what that is? So we know here in our definition, a gradient is a column vector, right? So a column vector multiplies by, and a column vector multiplies by the transpose of another column vector, that gave us an outer product, and that gave us a matrix. So that's what we need here. So we will have partial, so yeah, that's the matrix, but here we just have the jkth entry. So that's actually partial k, partial beta j. What we have over there, yi mu I, we are writing the scalar form, times partial k, partial beta k, yi mu I. These two are scalar. And now we just use the chain rule again, just as we have here, right? We need to have partial mu I, partial beta j, partial mu I, partial beta k here. So we'll keep them here. So finally, this result will be 1 over v mu I, and we'll have x ij, x ik. Okay, so that will be the jkth entry of the Hessian. Jkth entry of Hessian. That is, we can write it as just, probably I can write it as d square k yi mu I d beta square, right? This itself is a P by P matrix. So these properties are very interesting because they are just a generalization of what we have for the log likelihood. And we also have this for the GLM using the log likelihood. So this shouldn't be something surprising to you, but I think it's a good recap for our information. And also, if you recall, we have seen something similar in our IRLS algorithm. So something like this. This is the weight. This is the xij, xik. So that's actually part of what we call X transpose WX. That's there. Okay, and also something interesting to know is this. So we have, I would say, I will give this corollary. Yeah, I'm not going to show how the properties are derived. The details are in the notes. You can check it out yourself. So the corollary is this. If we encode the Fisher information using the quasi likelihood, it is that the quasi-Fisher information is no bigger than the actual Fisher information. So what I mean is this. So the expectation of partial square, partial mu I square, yi mu I. Okay, this is what we call the quasi-Fisher info. Okay, this is no greater than the actual Fisher information, partial square log likelihood of mu I. Okay, this is the Fisher info. How can we show this? So the direct proof is based on what we call the Cramer-Rao inequality. The Cramer-Rao inequality says that it's a very classic result in mathematical statistics. What this says is that for any unbiased estimator of a parameter, it gives you a lower bound on its variance. And that lower bound is given by the 1 over Fisher information. So we know that here, yi is an unbiased estimator for mu I, because that's the definition of mu I, right? So given that yi is unbiased for mu I, Cramer-Rao inequality applies. So we have variance of yi, which what we call by notation v mu I, okay? And now, based on this property, the v mu I is just 1 over this quasi-Fisher, okay? So it's 1 over the quasi-Fisher. Yeah, I'm just writing the words for simplicity. And the lower bound provided by Cramer-Rao is that this variance is no smaller than the 1 over the actual Fisher. So you have this inequality, and then you take the inverse on both sides. You can see quasi-Fisher is no greater than actual Fisher. So yeah, this is something interesting to know. And it also makes a lot of sense because, you know, quasi likelihood is something we just proposed for easiness, for simplicity, but it is not the actual log likelihood. So the best you can do is to have the quasi likelihood equal to the log likelihood. Then this Cramer-Rao inequality actually holds, right? Because when you're using the actual likelihood, log likelihood to obtain to do the inference, then we know that we have the MLE, and that's the most efficient. But here we are, and that's just the best unbiased estimate if it is unbiased. Okay, if the MLE is unbiased, then we know Cramer-Rao inequality ensures it is the most efficient estimator. But here we are not using the actual log likelihood. Instead, we're going to use the quasi likelihood. So we know that we cannot do better than the actual log likelihood. Okay, so that's the interesting thing to know. But for implementation, we're going to continue next time about how do we use this quasi likelihood to help us do extra-Poisson regression and to get rid of the constraint that the variance of yi equals to me. So we hope we can do that next time. All right, so thank you. And that's all for today.